Good morning, everyone. Welcome to the webinar organized by Digitode and TMYTEK titled Education to Advanced Prototyping, Bbox, and we'll be discussing proven mmWave testbeds for 6G research today. So we'll give it a few more minutes for everyone to join us. So we'll start at 11:03. So we'll give it 3 minutes for everyone else to join us. All right, it's 11:03, and I think it's a good time for us to begin. I am Anup Divakaran, a sales manager at Digitode Technologies. Thank you for everyone for tuning in to our live webinar. Let me introduce you to our audience. The speakers that we have. So we have 3 speakers during this webinar. We have Rohit Prajapati is the managing director at Digitode Technologies. We also have Vincent Lee, a sales manager from TMYTEK. And we also have Satvik with huge experience in wireless technologies. He is an application engineer from Digitode Technologies. All right, I'd like to set the stage and hand over to Rohit.
Hello everyone, I am Rohit Prajapati from Digitode Technologies, and it's a pleasure to welcome you to today's launch webinar in collaboration with TMYTEK. Today we are discussing something extremely important for the future of wireless engineering, how we move from education to advanced prototyping using real mmWave platforms. At Digitode Technologies, we focus on accelerating the journey from research concepts to working engineering systems. We support academia and R&D teams through advanced platforms and solutions across next-generation wireless research, FPGA development systems, quantum technology platforms, test and measurement ecosystems, and AI-driven embedded systems. Our core mission is simple: enable engineers to move faster from learning and simulation to real experimentation and deployment. So, wireless technology is no longer limited to conventional 5G deployments. We are entering the era of 6G advanced, 6G research, integrated sensing and communication, and NTN-IoT, where ecosystems must operate across terrestrial and satellite environments using mmWave MIMO and beamforming architectures. This evolution demands a major change in how engineers are trained. Simulation alone is no longer enough. Engineers must work with over-the-air hardware-based testbeds. This is exactly where the Bbox 8x8 Duo platform from TMYTEK comes in. It provides a modular mmWave MIMO testbed that enables real beamforming experiments, over-the-air validation beyond simulation, hands-on understanding of RF behavior, and system-level research for ISAC and 6G NTN applications. When combined with NextGen Wireless Educational Kit and structured 6G NTN-IoT course, this becomes a complete pathway from classroom concepts to simulation to OTA experimentation and research prototyping. This continuity is what modern wireless education has been missing. Through this collaboration between Digitode and TMYTEK, we aim to make industry-grade wireless research platforms accessible to universities, researchers, and advanced labs. Our focus is not just learning theory, but enabling institutions to build their own personal, future-ready wireless R&D ecosystems. Now, in today's session, what the participants will gain. So there will be an understanding on how to transition from simulation to OTA testing, architecture of modular mmWave MIMO systems, how educational labs can evolve into research prototyping environments, and exploring concepts like ISAC and 6G NTN-IoT. So we are very excited to bring you this webinar and the launch of this product in collaboration with TMYTEK. We hope this session will open new possibilities for your labs, research, and wireless innovation journey. Thank you for joining us. Let's get started.
All right, thank you, Rohit, and also thank you for all the digital team to host this webinar. And it's my pleasure to join this webinar again. My name is Vincent from TMYTEK. So remember, this is our second webinar since last year. The previous webinar, we talked about some features about 5G. So today we are going to to introduce something new about 6G. So the key differences between 5G and 6G, there are three key terms or three key topics we wanted to highlight during this webinar. The first one is satellite communication. So right now, everybody knows SpaceX or Starlink, they use LEO, MEO, GEO, different satellites to cover the area which was not covered by the base station. So satellite communications, everybody should heard about it already. And then the second topic is the RIS, so reconfigurable intelligent surface. Right now, we can also use the RIS, so we already commercialized the RIS. So we can use the RIS to try to redirect the signal to the area which was not covered as well. And then the third one is joint communication and sensing. So in 6G, we are now even talking about terahertz. So millimeter wave or terahertz, it has much higher, wider bandwidth. And then thanks to wider bandwidth, we can precisely use the beam to localize and also try to sense the target. So satellite communication, RIS, and also joint communication and sensing is the topic we want to highlight today. So we need all bands. We know FR1, FR2. So in the previous webinar, we talked about our FR2 platforms. So we have a different products in FR2 band, including the frequency converter and also the beamformer. And here we are going to talk more about FR3, which is the upper mid-band, the band in between FR1 and FR2. So in FR3, from 6 to 24 gigahertz, you can still have much more bandwidth compared to FR1. And then it has better frequency coverage than FR2. So this is the band we are going to use in the next years. So in the FR3 band, we have a new frequency converter. So this is a frequency converter we call Bbox 6 to 30. It means the frequency converter, it can cover from 6 to 30 gigahertz. So if you look at the picture here, the frequency converter, it's also a dual channel version. So you can use both channels for up conversions, for down conversions, or one for up, one for down. And so it's actually pure a mixer. So that's why you can use this frequency converter to do up and down conversion as well. And then this frequency converter, you can see there's a LO synchronization port. So this is a frequency converter. You can synchronize multiple frequency converter all together. For example, if you want to use this one with USRP X410 or X440, then you can use multiple frequency converter. For example, 2 frequency converter, you can have 4 channels. And this is a new feature. You can synchronize multiple frequency converter, and then they can be also they can remain phase coherent and also frequency coherent as well. So this is a new frequency converter we designed for FR3 band. And as you know, we also have frequency converter we call UDBox 5G. It covers from 24 to 44 gigahertz. And today we have this new frequency converter from 6 to 30. And now we're also designing another new frequency converter. It can cover from 17 to 53 gigahertz. So even higher frequencies and also wider band. All right, so the second one is we call new frequency. So the new antenna we call 8x8 dual. This one is actually we integrate our beamformer and also the frequency converter into one module. So it's more compact. And you can see there are some key features, new features, IF ready, and also some new control interface. So IF ready means we already integrate the frequency converter into this beamformer. So you can connect this device directly to the USRP system. So the IF range, it covers from 5 to 8 gigahertz. So you can actually just feed an IF signal into this beamformer, and then the frequency will be upconverted to FR2 band. And then you have this new 8x8 antenna module. So the previous version of the beamformer, we had 4x4 antenna module, but right now, this one, it has a larger array, which is 8x8. Okay, so I've IF ready 8x8 antenna module. It also supports dual polarization. So that's why you see you have 4 ports, 2 transmitters, 2 receivers. So with the USRP system, so we can see how it works. So here you have USRP X410, and then you see X410, you can generate 2 different data streams into this new 8x8 beamformer. So you have 2 signals, 2 different data streams, and each beamformer, it can generate 2 different polarization as well. So you have 2 beams, you can be pointing to different directions. Based on this 4x4 MIMO testbed, you can do, of course, MIMO, but you can also do joint communication and sensing. So this is a topic we wanted to highlight today. So with a USRP system, and this is a scenario you can use with our beamformer. So you can see there's a target. So you have 1 data stream, 1 beam, you can be pointing to the target. And then the second beam, it can also try to do, it can be used as a comm beam, communication beam. So there are different scenarios, there are different research you can use with our new 8x8 beamformer. But later after this, after my presentation, we are going to show you several videos regarding how the other universities, they use our beamformers for joint communication and sensing, and also other videos about the REIS. So this is a REIS, reconfigurable intelligent surface. Now we have 3.5, 4.7, and also 28 gigahertz. So the REIS, we call dynamic REIS because you can control the incident angle and also the reflection angle. We have 3 versions, 3.5, 4.7, and also 28 gigahertz. So the REIS is based on the pin diode. You can see, for example, this 4.7 gigahertz REIS, you have 16 by 16 antenna elements. So each antenna element can be controlled individually. It's a 1-bit system. So you can control 0 and then 180, so on and off. So you can see we also have controller. So controller and REIS, they are separate items. Why? Because the REIS is actually a scalable structure. We can combine 4 different REIS altogether into a larger array. We can even mix the frequency. It means the first REIS can be 3.5 gigahertz, the second REIS can be 4.7, and then we can also use another REIS running at 28 gigahertz. So each controller, it can control multiple REIS altogether. Right. So currently we have 3 different frequency coverage, but now we are also designing a REIS in FR3 band. We are still deciding which frequency we are going to design for FR3 band. So if you have any comments, you can also type into our chat here, because we are now collecting different feedback from universities. If you want to do, for example, 7 gigahertz or 10 gigahertz or 12 gigahertz, just feel free to write it into our chat so we can collect more information. Okay, so yeah, this is my part, and then we are going to show you different videos regarding joint communication and sensing, and also how to use our REIS, the scalable structure. Okay, so thank you for your time.
Professor Sunwoo Kim, Director of the Byunji Global Innovation Center at Hanyang University in Seoul, South Korea. At Byunji, we develop not only innovative ideas, but also implementable and practical solutions for next-generation telecommunication networks. Integrated Sensing and Communication, or ISAC, is one such solution. With our ISAC prototype demonstration, we show that radar-like sensing can be achieved using modern cellular equipment and communication waveforms.
Hello, my name is Adam Dubs from Hanyang University. I'm a part of Professor Kim Sun-woo's laboratory, and the solution we have prepared is a ISAC, Integrated Sensing and Communication demo, that shows real-time both communication and sensing components here. Well, on the far left, we have the Palm constellation indicating that communication is occurring, and that's part of the line of sight beam. And then on the left heat map here is the TX beam sweep, and then on the right is the RX beam sweep, with the range being shown in the y-axis. And so this big peak here, this bright spot indicating bright power, is a line of sight component that occurs and is used for communication. And then these non-line of sight components refer to non-line of sight components. So this is how you can do sensing to test the environment. So in this case here, it's not shown in the frame currently, but this non-line of sight component here is part of a monitor that's being reflected over in the corner there. And so if I just walk over here and I block non-line of sight component, then it disappears from the point of view. If I stand here with the reflector and move it, you could see a different non-line of sight component. But basically the solution that we're trying to solve is with millimeter wave components, we are looking for high resolution sensing in many applications, but also importantly to improve communication. So by determining strong non-line of sight components, you can improve the communication aspect. So our testbed that uses TMYTEK's Bbox 1 and Bbox Lite is looking at how can we do beamforming to do fast beam steering in order to collect channel impulse responses in multiple beam pairs and create the actual radar images.
Remember to subscribe, like, and ring the bell.
As we move towards 6G, dynamic RIS is redefining how signals travel. With active control, each RIS element can precisely reflect, steer, or focus millimeter wave signals. Let's take a closer look. We set up a typical L-shaped corner reflection scenario. At the transmitter side, Bbox 1 sends RF signals. The UD-Box 5G handles up conversion to millimeter wave, while the NIPXI VST system generates the signal. The signal hits the RIS, which is now in a 2x2 array mode, extending both range and coverage. It then reflects toward Bbox Lite, down converted again by the UD-Box 5G, and analyzed by the PXI VST. Here, we can clearly see performance through real-time data. With WebTLK, we can combine RIS tiles into larger arrays based on distance and easily adjust the reflection angle. Now we switch to a 1x2 array. This shows how different setups impact signal behavior and how flexible dynamic RIS can be. RIS offers hybrid band advantages, enabling seamless switching between FR1 and FR2 bands. With just one controller, users can easily reconfigure the system for different frequency ranges. Dynamic RIS unlocks a software-defined environment, enabling more efficient and controllable millimeter wave communication.
Remember to subscribe, like, and ring the bell.
Yeah. Good morning, everyone, and welcome. I'm Satvik from Digital Technologies, and today I'll be taking you about advancing 6G millimeter wave testbed and phased arrays. This session will focus on how practical, open, and scalable millimeter wave platforms are enabling real-time 5G FR2 and future 6G research. So, to start with a quick intro, TMYTEK is a global leader in millimeter wave. phased array antennas, and frequency converters. Founded in 2014, the company focuses on solving real-time millimeter challenges across 5G, 6G, satellite, radar, and defense domains. With strong R&D focus, global patents, and partnership with Tier 1 technology leaders, TMYTEK has become a reliable platform provider for advanced research wireless. Now, let's talk about our antenna array operating at 28.9 GHz. These aren't just array antennas. They come with configuration of 4x4 or 1x4, equipped with 6-bit phase shifters. This means precise, agile beam steering, crucial for overcoming those pesky millimeter wave challenges. Plus, with the support of FR2, N257, and N260 bands, these arrays are ready for forefront of wireless communication standards. Moreover, beam control software is already up and ready to go. You can control the beam using any engineering languages you prefer, including LabVIEW, Python, GNU Radio, C, C++. The Bbox offers superior RF performance across 24 to 44 GHz with adjustable IF ranges. It integrates seamlessly with HDRs using Ethernet or SPI control and supports popular programming languages again like Python, GNU Radio, LabVIEW, C++, making it highly suitable for open source and academic research. So coming to UDP0630, this is a frequency converter for the FR3 range. And the IF frequency, what we will feed from software-defined radios or any signal generator will be from 1 GHz to 10 GHz. And the RF frequency from the frequency converter is 6 GHz to 30 GHz of frequency range, which is the partial FR2 and FR3 range. So these are programs of Ethernet port with the help of TMX Lab, which is a TMYTEK's web-based GUI. So we talk about 6G vision and test beds. When we talk about 6G, key enablers include FR3 operation, beam tracking, RIS, AI native RANs, and open HDR ecosystems. TMYTEK's testbed are designed with these exact requirements in mind: scalable, software ready, and cost efficient for real deployments. Now we'll see 6G testbed and its architecture. So this slide shows a purpose-built FR3 testbed using Bbox 0630 and USRP X440. It converts wideband bandwidth, multi-channel coherency, and open source frameworks like GNU Radio and OpenAir interface, making it a known good starting point for 6G midband innovations. The software uses open source, and the baseband unit will be USRP X440, and the frequency converter will be UDP 0630 to achieve multi-channel connection, low deviation, phase coherence experiments. The experiment results are shown below. When the IF rises to FR3, RF signal is below 0.01 radian. This data is very advantageous for FR3 research, radar, defense, and SATCOM research. So next, we'll see the FR2 testbed. So the FR2 open air interface millimeter wave reference architecture. So this is one of the highlights here. The world's first integrated millimeter wave SDR and open air interface platform for both sensing and communication. By combining phased arrays, software-defined radios, and open-air interface, this setup enables real-world FR2 experiments for greater node D, user equipment, ISAC, and beamforming research. So this slide illustrates the 5G FR2 open-air interface architecture, showing a complete practical millimeter wave GNB to UE setup built on an open and commercial complex. The open-air interface-based CN core network and GNB handles the 5G protocol stack and connects the USRP X410 via high-speed SFP or UHD drivers, where the digital baseband is converted to IF. The IF signal is then passed to the 5G FR2 RF front-end, which performs the millimeter wave up or down conversion, amplification, and beamforming using phased array antennas. With control handled through the SPI and GPIO, on the receiver side, the over-the-air FR2 signal is captured by FR2Es, which can be USRP-based X410s or future courseware, commercially off-the-shelf UE or UE modules. So enabling realistic experimentation with 5G FR2 over-the-air experimentation. So these platforms support a wide range of use cases like FR2 and FR3 beam tracking, RF data recording, ISAC radar experiments, live HD video streaming, MIMO development, ultra-fast channel sounding, and even outdoor LOS testing at 28 GHz. So here we are showcasing the RS-based beam tracking use case, where a reconfigurable intelligent surface dynamics and steers millimeter wave signal to maintain a strong link between the transmitter and receiver. In this setup, the RIS adapts its own configuration in real time based on channel feedback, allowing the reflected beam to track changes in the user position or environment. This enables reliable millimeter wave communication even in non-line of sight scenarios, highlighting how RIS can improve coverage, enhance link robustness, and support advanced beam management techniques for 5G and beyond 5G wireless system. So coming to this use case, the RF data recording where the wideband RF signals are captured in real time and stored for offline. The waterfall and spectrum plot show how signals evolve over frequency and time, allowing the user to record real-world RF environments, including interference, burst transmission, and transient events. This capability is especially useful for post-processing, algorithm development, machine learning on RF data, and validation of communication or sensing systems. So coming to the last use case. So this is the ISAC radar use case, where the 5G millimeter wave hardware is used for both communication and sensing in a TDD manner, the time division duplex manner. The system analyzes the model 5G channel state information while alternating between communication signals and radar style pulse wave, enabling joint communication radar operations. By using advanced waveforms such as OTFs, the setup can demonstrate how a signal waveform can support both data transmission and environmental sensing, while also highlighting practically trade-offs like interference, bandwidth limitation, sensitivity to channel condition, and increased channel processing. So now we will see the education and setup from the TMYTEK, which is called as NextGen Wireless Education Kit. For universities and training programs, TMYTEK also offers NextGen Wireless Education Kits. These include structured lab covering beamforming fundamentals, DVB-H2, channel modeling, interference analysis, NTN-IoT, and hands-on millimeter wave system prototype. Yeah. So this slide shows the NextGen Wireless Education, which provides a complete end-to-end millimeter wave system starting from baseband generation in a software-defined radio, upconversion to a UD board, transmission via the RF front-end and the array antenna, and reception through amplification and down conversion back to baseband for analysis. The setup closely represents how a real-world millimeter wave system and enables hands-on learning of key concepts such as link budget, channel gain, constructive and destructive interference, beam steering, beam pattern measurement, and coherent reception using a shared link local oscillator. With this single platform, users can build and study 5G FR2 testbed, SATCOM Ka-band testbed, radar digital processing testbed, and also they can develop algorithms on millimeter wave system prototyping. So this courseware built around the platform, combining both strong theoretical foundations with hands-on laboratory experiments. The beamforming 101 module introduced core concepts such as link budget, channel gain, constructive and destructive interference, beam steering, field pattern measurement, and receiver phase alignment, helping students to build an intuitive understanding of antenna arrays and spatial signal processing. In addition, the optional NTN-IoT communication module focuses on satellite-based links and DVB-H2 or DVB-2X technologies, covering encoding, modulation, waveform generation, channel and interference simulation, and end-to-end transceiver experiments, making students to understand the NTN-IoT domain. So next, we'll be showing a demonstration on NTN-IoT.
Hello everyone. Today we introduce the Satellite Internet Experimental Platform. The Satellite Internet Experimental Solution was co-developed by the Fudan University team and IECUB. It is designed for experimental courses in satellite networks and satellite communications for computer science and communication majors. Next, we'll use a video transmission demo to show how the platform achieves simulated satellite-to-ground communication. The satellite simulation platform can realize an end-to-end ground station satellite-ground station link. This experiment demo only shows satellite-to-ground station data transmission. First, we see a VirtualBox virtual machine here, sending live streaming data via UDP and connecting to the Digital Twin Systems Delhi ground station. The data is uplinked via the space-to-ground link, forwarded via the inter-satellite link, and finally reaches the satellite above Tokyo. Then, the data is forwarded by the Digital Twin System, encoded and modulated with the DVB protocol, transmitted via USRP, and the signal is upconverted by the mmWave component, shifted to the high-frequency band, and transmitted by the phased array antenna. It is received and down-converted by the receiving antenna of the ground station on the right, and finally parsed by the NI-USRP. Here, we can see the data parsed by the VirtualBox connected to the Tokyo ground station, and the parsed video is displayed above. The Satellite Internet Experimental Platform includes the Satellite Internet Digital Twin System, SDT, USRP, and mmWave experimental components, and can simulate different layers of satellite internet, including the network layer and physical layer. First, let's introduce the Satellite Internet Digital Twin System, SDT. It includes online educational resources, covering course objectives, content, and specific experimental operations, including the experiment's background, principles, and steps. The platform also provides a visualized network layer simulation page and programmable online documentation, offering intuitive, easy-to-demonstrate advantages suitable for fundamental satellite internet teaching and beginner learning. The accompanying teaching resources include constellation simulation, satellite selection algorithms, inter-satellite link, and satellite end-to-end simulation experiments, etc. Advanced project-based experimental resources have also been developed, covering the network layer and physical layer of satellite internet. First, let's demonstrate how constellation simulation is achieved. The SDT teaching version provides editable dynamic documentation. Users can directly modify parameters, edit code, and verify results. Let's run the corresponding code here. Adding a new constellation. We can see the constellation we just designed. In addition to the teaching version, the SDT system also offers a research version. Based on containerized management and modular design, it provides researchers with a high-precision satellite simulation platform, capable of complex simulation of LEO satellite networks, supporting deep algorithm research and validation. The physical layer experiments include USRP equipment paired with mmWave antenna components. Using experimental programs developed on the Python platform, it simulates the signal transmission process between the satellite and the ground station.
Remember to subscribe, like, and ring the bell.
All right, team, the Q&A session, we'll be opening up the Q&A session now. For any questions that you may have, feel free to key in your questions and we'll be happy to answer them for you. And we also saw a question regarding the recording. Yes, we'll be sharing the recording of this webinar with all participants later this week. All right, the Q&A section is public now. You'll be able to ask your questions here. All right, we have a question from Tilak. What are the military applications of these in context of sensing? All right, Satvik, can you take this?
Yes, enough. I'll be answering that.
Right. We have a question from Lakshman. So what type of research activities can be carried out using TMYTEK NextGen Wireless Communication Kit? Excellent question. So we'll answer that, and also we'll be sending all of you more details regarding the communication kit, which talks about the list of experiments and many more details explaining how you can use this kit. All right, so we have answers to the question from both Ayush and Satvik. So with TMYTEK NextGen Wireless Communication Kit, you can do beamforming, beam steering, ISAC, mmWave radar sensing, and many more. And you could also do 5G FR2 testbed, satellite Ka-band testbed, radar testbed, beam tracking applications, and so on.
With the help of the beamformers, UD converters, and your USRPs basically as a baseband unit.
Thank you, Satvik. All right, I'm not seeing a lot more questions pending, so I will go ahead and leave our contact information here, so you can go ahead and email us your questions if you have any further. If you have any further questions, you can email us at contact@digitotech.com. We'll be happy to answer them for you. And also for everyone who attended, we are also going to be a part of National Conference on Communications. That's NCC 2026. That is towards the end of February at IIT Hyderabad. So we would be there for you, and you can meet us towards the end of February 26th onwards. All right. I thank everyone for joining today's session, and you can await more details regarding the next upcoming session from us on digitot.com. Thank you for joining in, guys. Thank you, Satvik and Alex, for your presentation and for answering the questions.
Thank you.
Yeah. Thank you, team.